Hello. Today is day 2 of Unit 14. We're going to talk about dynamic equilibrium. So if you checked out the Google Classroom, you are supposed to watch that 6-minute video on an equilibrium demonstration first. So if you have not done that yet, go do that because you won't have any idea what I'm talking about until you do. Okay, so let's just get started. So the word dynamic means a system is in motion. So that basically means it doesn't stop. The forward reaction goes and the reverse reaction goes, and they go at the same time. So if the forward and reverse reaction processes of a reversible reaction are occurring, that's considered to be a dynamic reaction. And then once the reverse and forward reactions occur at the same rate, then the reaction is at equilibrium. Okay, so in the demonstration, the guy that you were watching had 2 buckets or 2 Tupperware containers. One had water in it and one did not. So the one with water in it was your reactants, and the one that did not was your products. You can even try this demo at home. It's pretty simple. I just didn't have time to do it with the little guys around. Okay, so basically you take your 2 cups of equal size and you're just going to transfer water back and forth. So like reactants make products, at the same time products make reactants. Okay, so the forward reaction is turning reactants into products. That's what you should have seen. The reactant water went into the product bin. And then at the same time, the reverse reaction was the products turning back into reaction. So where is equilibrium reached? So this was the graph he showed you. So the forward rate was going fast at first, then slowed down. The reverse rate was going slow at first, then sped up. And then equilibrium was reached right here, where the rates became equal. Okay. So in the next trial, he put the water back in the reactant side, and then he changed his cups. So he had a big cup and a little cup. The big cup was transferring water from the reactants to the products, and the little cup was transferring water from the products back to the reaction. What happened was you ended up with the amounts not being equal in the same way that they were in the first trial. So he then showed you this graph with amount. So amounts on this side instead of last graph where it was rate. Okay, so this graph represents amount instead of rates as in trial 1. Remember in trial 1 that the rates had to reach equilibrium to become equal. Okay, so in this case, draw a line where equilibrium is reached. So it's the same idea, except the lines aren't going together the way they did in the last graph. So basically from this graph, you can see that the amounts or concentrations do not have to be equal, but you'll notice that they remain steady. So they become constant. Okay. All right. So I thought that was a good demonstration. We would have done something similar in class. But yeah. Okay. So let's move on to the notes. And we don't have a lot to do today. Oh, I forgot about these questions. Sorry. Okay. So equilibrium. So based on what you saw, equilibrium applies to reactions that are reversible, so go in both directions. In a dynamic equilibrium, as reactants form products, what does the product do at the same time? Product forms reactant. So reactant forms product in the forward, and then the reverse the backwards arrow, product forms reactants. Does the reaction ever stop? No. The forward and reverse reaction continue to happen once equilibrium, I'm just going to write EQ, is reached. So it never stops. It's going to just keep going and going and going until it runs out of stuff. So that would be a situation like if you had gases and it was in an open system, eventually the gas would be gone. Assuming that nothing is really changing, it's just going to keep going. Okay, describe what happens to rate in an equilibrium. Rate of the forward and rate of the reverse become equal. Equilibrium, equal. What happens to concentrations? They become constant, meaning they don't change. So they are not equal, they just level out. So that's a big distinction. All right, now we'll just do the quick set of notes. Okay. So this is on page 4 at the bottom. Okay, so in a reversible reaction, RXN reaction, the conversion of reactants to products and the conversion of products to reactants occurs at the same rate, so the same speeds. So as a reaction proceeds, the concentration of reactants, and we represent concentration by using these brackets, will decrease. So you start out with a lot of reactants at first, and then the concentration of the products will increase. So you start out with 0 products at first, and then you make a bunch of the product. And eventually you can reach chemical equilibrium. So there's a couple ways that this will be shown. So concentration, I'll just do like this. So if you have reactants, oh geez, that's not a great line. Okay, so reactants decrease, and so this is reactants, and products increase. So equilibrium is reached where the amounts level off. It should probably be a little bit over this way, but you get the point. Or it could look something like this, concentration on the side, time would be on the bottom. So reactants could go down like this, products could go up like this, and then equilibrium would be reached where they level out. Okay, so you could also have it look sort of like this, where they become equal, but that's not necessarily the case. So the products and reactants do not have to be equal. They have to be constant, meaning they don't change anymore. Okay. All right, so in a chemical equilibrium, that should say 3 things must be true. The first is that rate of the forward reaction, and forward means like you read the reaction left to right, has to equal the rate of the reverse reaction. Concentrations, which is just another way of saying amount, becomes constant. So think about like concentration, constant, they both start with CON. And it must be in a closed system. So what that means is basically you need to have a lid. So if the regents, well, we're not taking the regents, but you will have a final, were to ask you, how could you make this a closed system? You would say, add a lid. Okay, so physical changes can also be at equilibrium. We were just talking about chemical reactions. These are 3 physical changes. So water at 0 degrees, remember physical changes can be reversed. So at 0 degrees, we have melting and freezing. So that means the rate of melting, and since we're at equilibrium, it has to be equal to the rate of freezing. Okay, it's on the table, go get it. And then at 100 degrees, the rate of boiling has to equal the rate of, the opposite of boiling is condensing. If I was technical, I would say vaporizing. Okay, and then in a saturated solution, remember, saturated solution is holding as much as it can, and it also has stuff on the bottom that it can't hold. All right, so the rate that one dissolves has to equal the rate that one comes down and crystallizes. So the rate of dissolving equals the rate of crystallizing. And that's it for this section. Make sure you're watching the video and not just sharing your notes with friends. I saw that the views are pretty low, which makes me feel like not everyone's watching these. Just kind of not the point. And then also tonight you're gonna have a homework on a different platform. So do your best to you know, sign in how I think they ask you to sign in with your Google account. So just do that. Make sure you write your name so that I can see what you're answering. And we'll see if that works out, then I might continue to do it that way with the homework. Okay, so I will talk to you guys tomorrow. Bye.